All right. Let's go. So I figured I'm gonna post Quantum Crypto Wallet. I'm bored, out of my mind. This is a way for me to keep track of my progress, my streams. Let me go ahead and share my screen. All throughout, where is it? Here we go. Window. Tweet. There we go. So yeah, I kind of just. That's fun to look at. It's fun to look at. All right, that's pretty fun to look at. That's fun to look at. Yeah. So, anyways, lattices. I'm gonna be using this. I guess this course. I'm also going to be using. This is a great book that I've been keeping track of. Great book by Michael Welschenbach. I know I'm mispronouncing that, but shout out to this guy. Hold on, is there a way I can? There we go. So I'm just going to keep track. I'm an undergrad student. I'm a sophomore. So yeah, I'm just trying to keep track of what I'm doing. Hopefully this works. So let's start. Okay, we're at the very beginning. So let's go to where we were. Yeah, okay. Mathematical background of a lattice. Okay, so unpacking this. Lattice is a subgroup. I need my glasses. Do I? Not but this should block your mind. Oh, I'm tired. It's 11:30 at night. So this is kind of rough. It's kind of rough doing this shit. So so looking at the subgroup, contains huh? That's interesting. That's interesting. I guess that makes sense. I took linear algebra last year. Isn't that one of the requirements for vector spaces and also bases in that regard? I don't fucking know. But yeah, lattices. Hey man, this will be pretty cool. It's like a cool, I guess, yeah, little side project to work on. So contains identity vector. Let's see, and for any x plus y, oh, not x plus y, sorry, x or y in L, negative x spans L, and x plus y spans L. Oh, that makes sense. That makes a little bit of sense, I think. Yeah. What they're trying to show you, they're just trying to show that you have some kind of lattice. Huh. Yeah, that's kind of tricky to understand at first, but it does make sense. So in other words, it's just saying for any x and y. So for any x and y that exists in that lattice, I'm trying to understand this. Negative x also exists in the lattice, and the addition of x and y is also in that lattice. Okay, that makes sense. The conceptual, I'm thinking of a lattice like almost like a square, but a little bit more perpendicular. I don't know. I'm considering like something like this. Like if this is my lattice, you guys can't really see. Oh, there we go. You see that? Yeah. Like if that's my lattice right there, any point above or below, or any point extended on here, any point, yeah, shit. Any point up or down, left or right would be on the lattice. So I think is what it's trying to say. So then when you would put all the pieces together, you would find that it actually works. So it's pretty neat. That's how I'm thinking about it at least. I'm not too sure. Let's keep going. Okay. Lattice. It is also discrete. What does that mean? It means neighborhood. Oh. That makes sense actually. That makes sense. That actually makes sense. I'm not looking at the form. I'm kind of looking at like the informal definition. Like I'm looking at this. Huh. That makes sense. Or sorry, this right here. That makes a little bit of sense because I think what it's just trying to say is like, okay, like in the previous example, in some coordinate system, this is R2. I think what it's trying to say, correct me if I'm wrong here. I think it just means so if, bro, this glare is so annoying. Holy crap. Dude, what in the world is this glare, man? Okay, oh, there we go. Oh, I can't give up. But it's, what we're trying to say is if you have, oh, wait. I'm gonna draw some stuff out as we do this. So if this is some lattice, what I was trying to say is there's some neighborhood. Like if I take this neighborhood right here, you can see only one point is on the lattice. That's pretty cool. Um, where am I? Where did my thumbtacks go? Did those just fall down? That's annoying. Wow. I guess they both fell down. Cool. No, not cool. It's gonna hurt later on. Let's step on them. I know I'm step on them. My luck. Oh man, fuck it. I have this one too, so I'll just use this one. That's cool. Anywho, let's get some music going. You guys can't hear. You guys can't see what I'm gonna put. But I'm gonna put some Glenn Miller. Better. Right. Anyways, let's go back. Okay. Let's look at the formal definition. So I'm just gonna keep going here. Okay. Now let's look at the formal definition. So it says formally there exists some. I, what does that even say? I can't, is that a symbol? I'm honestly kind of cooked with this stuff. Okay, there we go. So it's just some number such that such that this union. No, sorry, intersection. I'm tripping. Wait, what form? I don't understand at all. So I'm gonna break it down. I don't get that at all. That formal definition. There exists some value such that x plus that value times. Okay, I'm sort of understanding the bigger picture here now. But this is kind of hard. Okay, so I'm gonna write that in words. So x plus EB is the open ball rate. Oh, I see. We're gonna use the same example. Let's draw our lattice. Say x here. Oh, points in the lattice are here. So we draw. So it's like an open ball. Ah, I see. So this is just saying. So the math doesn't really make much sense at all, but the concept makes some sense. So you can see here in the bottom picture, there's like a little circle. This right here, this it's just saying. So if you take that example of the lattice being across in a 2D plane, right? Pick let's say the top point of the cross. You draw a circle around the top point of the cross. The theorem is, or I guess this is a theorem, yeah, something. The theorem is just saying that to be a lattice, there's some circle you must be able to draw around that point x, such that x is the only point in that lattice. And then the only thing that's intersecting that and this ball on the lattice is just x. So that makes sense conceptually. Um, Another one, and also group is condition is equivalent. The equivalent of E for zero spans L. I don't really know what that means. I don't know. I'm not really sure what that one's supposed to mean. Yeah, and this is the one L's group. It was just a single. Oh, I see. I see. I see. That makes sense. That makes sense. It's just all it's saying is just that if your lattice is a group, like the one I just showed you, the same value of E will apply to all points of the lattice. That's pretty cool. So let's look at some examples. Yes, let me some examples. So let's write some notes. So the singleton set, I believe. So I don't know how to read this. I took discrete math. This just means that there's the singleton set just means only one thing in that set. This is something good to look up. This is singleton set. I want to say it's only one element and it's just null, or is it zero? Maybe I'm wrong. Let's see. I'm kind of curious. Oh, never mind. Only has one element. Oh, I see. I get it now. Okay. It just means that it has one element. That's all it means. Let's just see the set of zero, mm, the space of zero, which is a subset of Rn, is a lattice. How'd you get that? How did you get that? Singleton set. Let's see why. Because I mean, it makes sense why a zero could be. Let's see if it passes. Yeah, see if it passes the first conditions. So let's take x is zero and y is also zero. There's only two elements we can pick from. The one. So x plus y is zero. Zero still spans zero. So this works. And then negative zero equals zero. Zero spans zero. Works. Testing to see if it's discrete, which it is. Because it's both a subgroup and it's also discrete. Or the distance between reads distance is zero. Cool. Dope. Okay, focus better. No, actually, why? I need these. Okay, so that one works. Let's plug it into the into the subset of R. So just the set of all integers. Well, that one kind of makes sense. It's almost too loud. Okay. Makes sense. For a one-dimensional lattice. So, first of all, how big is he? So there's these possible values. Negative 100, negative some random values. Let's choose x. Negative 1 and a y, arbitrary y. Ah, I see. X plus y in this subset? Absolutely. X plus y is 2. 2 is an element of C. Now just check. Oh, that's x equals negative 1. Negative x equals 1. 1 is also in the set of integers. So it works. Sick. So now we just need to make sure. Yeah, we just need to make sure this is. Make sure it's discrete, right? Oh, but it is. The distance between each element is 1. I'll call it UOP. It's 1. So it works. That's dope. So it is one dimensional. Okay, cool. And it says the Zn is an n-dimensional lattice. Oh, that's cool. That's cool. And it's the same reason. Okay, because for example, let's take z squared, right? Or, oh, wait, what even is that though? Okay, I'm not too sure actually. That's kind of tricky. Let's go ahead and let's go ahead. Let's talk to the forbidden fruit. Is I'm trying to understand this. Asian product. I'm gonna write this down. Zn is a Cartesian product. Oh, I see. I see. Ah, cool. So that one doesn't make sense. That makes sense. All right, let's go back. For any lattice, it's scaling. That's actually that's probably really important to remember. Any linear transformation. I forgot. We're gonna ask the forbidden fruit one more time. I almost. Oh, it's the multiplication and addition, right? Yeah. Okay. Cool. Okay. Okay. So I'm just gonna say recall scalar mult. Cool. And using that, let's actually analyze. Huh. So let's write this down. Any scaling. Huh. let's actually get. I want to write down an example to kind of let's like prove this. So let's say take z. Right, take z as a subset of the real numbers. This is the lattice. We just proved this. Let's scale this. So let's say three z. Lattice. Well, we just said this has to lattice has to abide in two key properties. First property must be a subgroup, be discrete. We just learned that. So let's see. Subgroup. Let's pick two arbitrary elements. So first is write down our potential elements. So we can have what? Negative 99, negative 33, maybe 0, maybe 9, maybe 36. Those are all possibilities, right? These are all scale multiples. So let's see. Let's choose x to be some arbitrary number. Let's say x is 5. And let's say y. Oh, wait, no, I can't say 5. That doesn't exist. X equals 3. Y equals negative 6. So if we see x plus y is negative 3. Negative 3 spans the lattice. So that condition works. Let's check to see. So x is 3, negative x. What is negative x? Negative x is negative 3, which also spans the lattice, as we just proved. Cool. So it's a subgroup. So now we just need a test to see, is it also discrete? And make sure I get that right. So this makes sense, and then is it discrete? Well, you tell me. The distance is 3. We just proved that. The distance between points is just a scale. Distance is just c. So it works. You see, I'm writing this all out. You feel free to use number 4. The set. Let's write down the set. X in all real numbers of z of n. So we're in n-dimensional lattice. That the sum between I equals 1 to n xi 2z. Okay, I want to first break down what's actually happening here. So the set. So this in easy language, this just means the set. This is every value in an n-dimensional lattice, and we're essentially inputting into this function here. This function is saying this is the sum of n hang on. This is the sum of this is the sum. This one's kind of tricky. Give me a minute. This one's gonna be kind of hard. This is not an arbitrary one. This is kind of a tricky one. Okay, what better way to do it than pick an example? Yes, let's pick an example. So let's say x in z2. Oh, shut up, you ad. I'll have an interview with them tomorrow. Shout out Granger. How about that? Okay. So let's just pick n equals 2. So our possible x values, well, there are many x values you can pick from. Zero, 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 one, one, zero, zero. All potential values, 1, 1. Those are all just values I'm picking from. For each value, we're summing up where x exists. Oh, where x is a multiple of 2. 2z. Oh, I see. Okay, so it's just saying, so for 0, 0, this is a checkerboard ladder, so that's kind of it's a nice clue. So 0, 0 should map. This should work. We'll just get 0, 0. 0, 1 will not 1. 1 does not exist in the span in 2 times a set of integers. 1, 0, same thing. 1, 1, same thing. 1, 2. No, that still won't work. Oh, I think what's happening is it's summing up all the x values and then seeing if that is spanning the set of two times the set of integers. So in that case, let's give some examples. So I know what the answer is. The answer is going to be 0, 0, 2, 2, 0, 2, 2, but I want to see why. So let's just make up some more points again. Let's pick 0, 0, let's pick 1, 0, let's pick 1, 1. Let's pick 2, 1. Let's pick 1, 2. Let's pick 2, 2. Okay. Let's see. For 0, 0, so in this case, I equals 1 and n equals 2, right? So it's going to iterate twice, right? So x1 is 0 equals 0. And does 0 span 2n or 2z? Yes, it does. So this is a valid point. 1, 0, 1. So we're going to take 1. So essentially, we're adding up and 2, 0 or 2x. No. How about 1, 1? Okay, this is where it gets interesting. We have 1 plus 1 equal to 2. And 2 does span the set of 2z, right? Because you divide it out, you get z equals to 1. The reason why 1 span 2z doesn't work is because you get 1 half span z, which is an inaccuracy. That's not an integer. So this works. 2, 1, that point. 2 plus 1 is 3. 3 does not span 2z. Does not work. 1, 2. 1, 2 equals 3. Does not span 2z once again. How about 2, 2? It's equal to 4, which does span 2z? It does. So our valid points, let's write them out. 1, 1, 2, 2. If I wanted to, I could even say 0, 2. Or 2, 0. I'll just draw this out. A nice little Cartesian graph. So here's the origin, 1, 1. Let's make the origin a different color. 1, 1, 2, 2, 0, 2. Wow, that's fascinating. Look at that. That's actually really cool. What? Wait, that's actually really cool. Look. So by doing it this way, you actually on this end you can see. Look at that lattice. Look what we ended up. Look what we ended up getting. So these points work. So in other words, you find the points that work. If they add up to 2, you include it in lattice, and it works. Multiples of 2 work, and this spans a lattice of the checkerboard. I've seen this one before, actually. I saw it in an old book. I don't remember it. What I'm gonna say. So I'm just gonna write. I'm just gonna take some notes here. Cool. Okay, dope. Let's look at number 5. 5, the rationals. That's pretty cool. Let me just make sure something really quickly, really fast. This for future note. I want to make sure this is okay. Cool. So rationals Q and irrationals RQ. 6, 6, 6, 6, 6. Okay. So this one makes sense. This one's pretty easy. Yeah, I can explain it. So this one is not a lattice because if we take a random number, let's call it Q1 plus a random rational plus Q2, you will get some QZ, whatever, some rational number, but the point is it's a rational number and it spans this set of rational numbers. So that works. The problem is it is not discrete because the spacing is not the spacing is not constant. I think that's how I'll explain it. Like for example, 1.999 to 2, right? The spacing is pretty small, but if I included 2.5, you see the spacing not constant. So it's no longer a discrete system. We just proved that in discrete. In this case, the E value would not be the same for both. And of course, let's go ahead and check. I want to make sure this is right. So talk to me about why the rational set is not a lattice. Use the discrete property and show why the rational set is not discrete. Okay, let's see. Mm-hmm. That's interesting. Okay, for the sake of this, I'm not gonna like look at the full theory. I just wanted an idea, and so it makes sense. So essentially, that if you didn't get that, um, I was half right, I believe. I think this is a valid reason, but I think the more I guess, the better reason it would be that between any two rational numbers, there exists Another rational number. That's really interesting. So, but that also makes sense because if you think about it in terms of a checkerboard or like the line as you see there, you can't really you can't make that with a rational number set because it's not. It just makes sense. 'Cause it's not discrete. You can't lay them out and see it that way. That's pretty interesting. Let's look at number six. Right, number six. What is the odd? Oh, interesting. Odd numbers. Yeah, 2z plus 1. Well, I know it says, but let's test it out anyways. So let's just take these set of odd numbers. So this could also span negative. So let's just take -5, -1, 3, 7. Okay, let's just say that testing set or whatever. So let's just take an x value, 3. Oh no, it doesn't satisfy the rule. That's really interesting. Oh, that's so interesting. Cool. That one makes sense, and that's when you add them together, you get 2, and 2 does not span, so therefore it cannot be a lattice. It's pretty interesting. I- I'm not gonna really look at that for now. All right, definition. 2.3. The rank of a lattice where L is a subset of Rn is dimension. I don't know if that's how it works though. You take the linear span? Maybe. Maybe. Oh my gosh, this fucking ass. I'm just looking. Okay. So, what does that actually mean? Linear span. Ah, the rank of the lattice is the dimension of its linear span. So it's the dimension of the span. So it's just, I guess, just how much it spans, maybe. It says here. Cool. Let me go back up to the last thing might be kind of important. I look at here. No, no, not really. Um, so I'm just gonna say, okay, so we're gonna, that's only important. Just know that the span is assumed to be full for every lattice. Is what I think it's trying to say. Cool. Okay, so we're gonna assume full rank. Of particular interest are rational and integer lattices, which are subsets. I thought we just said that the rational numbers cannot be lattices, though. Hmm. I thought we just said that lattices, rational numbers can't be. Maybe honestly, maybe if you find different conditions, you probably could form a lattice with those conditions. I have to do more digging in that. Okay. Oh, sorry. There it is. It says right there. We are interested. I'll say note. Right, and that was just proved in the last example. Cool. Up to scale, rational. Huh. I don't understand. Oh, there's so much content, bro. There's so much. But this is cool though. This is like cool stuff to learn. I feel like. Scale. Oh, I see. Ah, that's cool. So that's actually pretty cool. So what this is just saying here, all that's saying is that if you take a lattice, the irrational lattice is essentially an integer lattice scaled very down, or it's scaled at a very like fine level. That's what a rational lattice is. But the two, I guess, yeah, that makes sense. The two are kind of interchangeable when you consider them that way. So that's pretty interesting. Yeah, dope. So this last part. Rationality is important for different persons who understand. Yeah. So that's probably I'm probably bold that rationality. Cool. Lattice bases. Let's talk about lattice bases. New page. It's probably the last thing that I look at for the day. But it's very interesting. It is. It's very, very interesting. Definition. Right, that makes sense. Essentially, it's just okay. So that makes sense. It means all lattices span infinity, which is true. Right? We just saw that in the example of take all integers. They, that lattice spans infinity. Straight the not spans the entire lattice spans infinity. Whereas here we can say that we can represent a lattice with a basis to make it finite. So that's all I was trying to say here. So let's just look at this. A basis of a subset lattice. LB. Just copying it down for now. I equals 1 and okay. So I wrote down up until the end of I wrote down this definition right here. The linear independent vectors. Hmm. I'm trying to understand. C1, B1, such that C is an integer. Oh, I see. It's saying it's a okay. I see. Okay, okay. This makes sense. This definition, well, the definition makes sense. The definition is saying This right here is just this thing you see right here. This right here is just a fancy way of saying that this lattice is the sum of these independent vectors. So it's not really. It looks harder than it really is. That's what I'm trying to say. This actually makes this is a very simple definition. It's just saying, for example, if I'm in the R2 space, right? Easiest way to span a lattice, use the vectors 1, 0, and 0, 1. Those are the only vectors that we actually can use that are like that are linearly independent. You can choose maybe even 1, 1, 1, 1, 0, 1, right? That's a possible one. Now, would this form a lattice? Let's see. So this is B1, and this is B2. So LB is Z1, 1, 1 plus Z2. Now, would this actually be a lattice, though? This is our matrix. What reduces to 1, 0, 0, 1. It should be. Yeah. Just check here. Cool. Yeah, so I'm right. I was right. This is what I was showing. This is what I was. Um, Here's what I was, I guess, like talking about to kind of illustrate this better. See here. You can just create the formula for the lattice there. Use both vectors, put them into the formula, and then you get your LB. So it's pretty cool. Pretty cool how that works. And then yeah, so the good question to ask would be if the vectors are literally independent, does that guarantee this? My spelling is shitty, but this is see, interesting. Oh, see, so okay, that's actually a great question to ask. I'm glad I asked that question. Huh. Cool, cool, cool. Okay, so that makes sense. So I'm just gonna write this example down. I don't want to forget this. Very good counterexample. 1, 0, 0 pi. Literally independent, but not discrete. So it would not work. Cool. Let's keep going here. Interpret p spins. I'm not gonna focus about that. I think I got a good understanding from this definition here. A lattice always has a basis. Such a basis is not unique. Essentially, the existence of multiple lattice bases. Interesting. That's important to write down. I'm gonna write a lattice. Cool. Essentially, the existence of multiple. Determinant plus or minus 1. So actually, I had absolutely zero idea what this part means. So we're going to look at unimodular matrix. Unimodular matrix, the square matrix has a determinant. Right? We just Pascal matrix. What is this? So all ones in the diagonal. No, I lied. Binomial coefficients. Oh, I remember this. This is Pascal's theorem. That's Pascal's theorem. I don't know too much about it. Lower triangular matrix. Upper triangular. Interesting. Permutation matrices. What is this? Oh, yes. That makes sense. This stuff's hard. This stuff is not easy. It's not conceptual at all. I guess. All right, so let's go back to the forbidden fruit. Let's say, what does it matter? We know how to get it. What is it? Why does it even matter? Okay, why does it matter? Preserves the structure. That makes sense, but I still don't understand. Always invertible. Oh, so I'm gonna write that down. These. Dope. It's really cool. Okay. Of course, we'll get some more examples on that later as we get more advanced. We get more into this. We're like halfway through. Oh my goodness, this is gonna be. That's gonna be a lot. That's gonna be a lot to like digest through. Right, S prime equals. That honestly, I might just find the easy way to explain that because it's too much to think about. Although this does kind of make sense. Volumetric picture, this does kind of make sense. Hmm, interesting. Yeah, it could be hard. Not for the day, but I'm just gonna look through. I'm gonna look through some of the next. Okay, this one looks decent. Okay. Hmm. Oh my gosh, this is gonna be really fucking hard. You know what though? We can do it. All right, that's gonna conclude it for today, y'all. Everyone, take care. Good night. I'm gonna do it. I'm tired. It's like an hour of work. Try to do like an hour every day, roughly. It's gonna be hard. I'm a sophomore. One class I'm taking math related besides Calc 3. What am I taking? Linear algebra, discrete maths. That's it. So I'm kind of on my own here. But you know, I think honestly, with all this, we have so much information that's out there on the internet, ChatGPT, YouTube. We're gonna find ways to make it work. Yeah, because I want to understand this stuff. I want to make a good product. And I really want to. With that, bye everybody.